Hello everyone, I'm Shunsuke Yoneda of Tokyo University, Japan. Today, I'd like to talk to you about deep segmentation network without mask image supervision for 2D image registration. To solve the labor shortage in logistics, there is a strong demand for solutions in warehouses to automate the picking process of planar objects. Recently, some object picking systems using cameras and robot arms have been developed as one of the automation solutions. To control robot arms, we need to accurately perform the segmentation for predicting mask images, object recognition for predicting object classes, and pose estimation for estimating pose parameters. To do this, we consider 2D image registration techniques. In the first step, they detect interest points. In the second step, they extract local descriptors. In the third step, they search the correspondences between the interest points using the descriptors. 2D image registration techniques perform the object recognition and pose estimation tasks. The popular techniques of 2D image registration are Shift and Ranzek, ORB and Ranzek, and Superpoint and Superglue. However, these techniques don't consider how to perform the segmentation task. Here, we propose a deep segmentation network module. Our module is easily attached to the 2D image registration without mask image supervision. Before explaining our module, we consider a simple case to use a fully supervised segmentation network, in addition to using the 2D image registration. This case requires collecting large datasets with mask supervision. Mask supervision is generally costly to obtain high segmentation accuracy. Instead of the simple case, we introduce a weakly supervised segmentation network into the 2D image registration. Our module with no cost of mask supervision performed the segmentation task accurately. To train our network, we exploit the key idea of the canonical plane. The canonical plane is defined by the closest object plane from the camera position and the smallest angle calculated between camera's optical axis and object plane's surface normal. Our network performs the segmentation task using the output of 2D image registration between images belonging to the same canonical plane. Based on this idea, our training process can achieve no mask image supervision for the segmentation task. Let's get started on the detail of our network in the training process. Our network consists of 3 modules. The deep segmentation network module, the 2D image registration module, and the target binarization module. The deep segmentation network module predicts the query mask from the query. The 2D image registration module estimates the homography transformation matrix from the target to the query. The target binarization module predicts the target mask from the target. We explain the detail of the deep segmentation network module. Our module consists of 3 layers: the encoder layer, the merging layer, and the decoder layer. In the first step, the encoder layer extracts the feature from the query. In the second step, the merging layer combines the feature extracted from the encoder layer with the feature extracted from the 2D image registration module. In the merging layer, we consider highlighting the informative region of the feature, representing the canonical plane. In the third step, the decoder layer predicts the query mask using the feature combined from the merging layer. To check the similarity between the query mask and the target mask, we compute the mask loss. By reducing the mask loss, we can train the deep segmentation network module without mask image supervision. We explain our network in the inference process. Our network consists of 2 modules: the deep segmentation network module and recognition module. The deep segmentation network module is the same as in the training process. The recognition module performs the object recognition and pose estimation tasks in the same way as the existing 2D image registration. We evaluated the performance using fully and weakly supervised segmentation networks and our deep segmentation network. We used 2 background conditions: tray background and crater background. This table shows performances for segmentation accuracy, recognition accuracy, and pose error. These techniques are fully supervised segmentation networks. These techniques are weakly supervised segmentation networks. Fully supervised segmentation networks perform high segmentation accuracy and high recognition accuracy. Our network outperforms all weakly supervised segmentation networks in segmentation accuracy and recognition accuracy. Moreover, our network was the only one that was able to obtain pose estimation outputs. Our network is advantageous for not requiring mask image supervision. We show the qualitative results of our network. In the tray background condition, we show the input, the segmentation region, the transformation region, and the target. In further background condition, we show the input, the segmentation region, the transformation region, and the target. Our deep segmentation network module accurately works because the appearances of the object between the transformation region and the target are similar. To conclude, we propose a deep segmentation network module without mask image supervision. Our module is easily attached to the 2D image registration. We demonstrated our network accurately performs the segmentation, object recognition, and pose estimation tasks. In future work, we expand to evaluate the performance of our network on datasets of objects with various shapes. Also, we intend to develop a network for handling more complex transformations. That's all. Thank you for your attention.